Okay, here we have the last section of our Unit 9. It's section 2.5, function library and piecewise functions. The function library is mainly just a list of all the different types of functions that we should be familiar with, and so we're going to work on graphing those and what their shapes are and things like that. So that's our first goal, and our second goal is to be able to graph piecewise defined functions. That basically is functions that are put together by pieces of other functions. So we're really going to have to work with domain on this one and get really comfortable with the idea of domain and all that. Okay? Alright, so first function in our function library is a constant function, f of x equals b, where if I draw, if I draw right here, we go 1, 2. Let's say I draw that right there. That would be f of x equals 2. Because no matter what your x value, anywhere along the line, all these x values, their f of x is right here at 2, meaning their y value. Okay? So whenever you see an f of x equals a constant, a number, a real number, we have a horizontal graph. For f of x equals x, this should say slope, not slop. That's a line with a slope of 1, and I'm not sure why this didn't come through, but this is the line that we reflect our inverses by. Okay, so drawn here, change to red, diagonal line going through the origin, same rise over run, 1, 1. Okay, could be 2, 2, 3, 3, whatever. F of x equals x, we call this the identity function. All right, and our square function or quadratic function, made up of a parabola centered at 0, 0, and if I go out 1, I go up 1, and if I go out the other way 1, I go up 1, if I go out 2, I go up 3, 4. And the other side mirrors it. Okay? This kind of graph is mirrored about the y-axis. Okay? And if there is a positive value in front, like right now that would be a positive 1, then it points upwards. If you had, say, a negative 1, I'll do negative in red. If it was negative 1 in front, it would look like that. Alright. Our cubic function. Our cubic function is going to have the same sort of end behavior as a line, meaning we're going to end up having arrows that point like this and like this, if it's positive. If it's negative, it's just like the slope of a line. It changes the arrows to here and here. Alright, so that's kind of an important function, and that has to do with the fact that it's got an odd exponent of 3. Alright, if it's an even exponent of 3, then the arrows point in the same direction. And we're going to deal with more of this end behavior stuff when we talk about polynomials and things in the coming chapters. But the simplest way, I think, to get ourselves used to this is to kind of just put an XY chart together. So we have x cubed, 0, 0 cubed is 0. So our first point is the origin. Alright, 1, 1 cubed, 1. Interestingly enough, if we go negative 1, I always like to go a little positive, a little negative, just to kind of see the behavior of the function. Negative 1 cubed is also negative 1. So we start out here at 1, we go up to 1. We start out here at negative 1, we go down to negative 1. Alright? And if you continue on, we could try 2 cubed would give us 8, and negative 2 cubed would give us negative 8. Alright? So our shape looks something like that. So there's a cubic function. Kind of a curve, no real local min, local max, just kind of swoops on up. Alright. Our square root function, however, is somewhat different. See here in the cubic function, we have nothing stopping us from putting in any x value. I could plug in any x here and I would get out any y. So my domain for a cubic function, and all the functions I've done so far have been all real. But our square root function is the first domain that changes that fact. Because the square root function, what's the one thing we can't square root? Those would be negatives. So when I create my xy chart, x square root of x, y, I can't plug in a negative 1 because square root of negative 1 is I, and that's not graphable, at least not on a real function. So I need to plug in 0, 1, maybe 2, and I'm going to do 3 just for the heck of it. Okay, so square root of 0, 0, square root of 1, 1. Square root of 2 is about 1.4, roughly. Square root of 3 is about 1.7, roughly. So we got 0, 0, 1, 1, 2, 1.4, 3, 1.7. Just above 1.4. And this is going to go like this. So if I'm looking at this domain, nothing over here exists. So none of these x values give us anything. Anything in the negative wouldn't work. So my domain can only be all x's, provided that x is greater than or equal to 0. And your range for something like this would be the same. All y's, provided that y is greater than or equal to 0, because whenever you take the square root of a number, you're always going to end up with a positive. And that's kind of what you're describing with your domain and range here. Okay? So there's our square root function. If it becomes a negative square root, it just flips according to the x-axis, flips across the x-axis. So I can do that real quick in red here. It's going to be a little messy. Let me erase my range. It's going to look... going to look like this. And that looks like a parabola upside down, which makes sense because if I take an x squared and I square root it, then I get plus or minus square root of x. Okay. Or plus or minus x, excuse me. If I take an x and I square root it, I get plus or minus square root of x. So there we go. Alright. Moving forward. Okay, we got the cube root of x, which might seem a little tricky because you're thinking, oh, I just learned how to do the square root. Shouldn't the cube root be exactly the same? Well, it's not. The problem is that we have an odd index here. And with an odd index, what you have is you have the ability to cube root negatives. So when I create my xy chart, I get the cube root of x, and I go 0, cube root of 0 is 0. But then I try negative 1. Cube root of negative 1 is negative 1. Because if you think about it, negative 1 times negative 1 times negative 1 would give you negative 1 still. And so that's what you're kind of finding. And then cube root of 1 is 1. And you could do cube root of 2, cube root of 3, and all those things in the future, but they're all decimals. So I'm just going to draw the shape, and you can kind of get used to the shape. If you want to try, say, I don't know, like 27, you'd get the cube root of 27, which would be 3, and that would help you figure things out even further. But we got 0, 0, 1, 1, 1, negative 1, and so our graph looks like that. And again, our domain here is all real. Because look, our arrows point to forever. That's what the arrow means. Okay? And range, all real as well. Because there's no asymptote, there's nothing stopping our continuity. Okay, so we're going to do a reciprocal function. And first we can look at the domain and kind of see how this thing should look. But our reciprocal function has a domain where we have all x's, provided that x doesn't equal 0, because again we can't divide by 0. And so what that tells us is that we are never going to cross an axis. So because we can't have an x equal to 0 with this function here, we also can't ever have an f of x equal to 0. So what happens is we end up having two asymptotes. One at f of x equals 0 and one that x equals 0. And then if you draw or do a couple different values here, you try maybe some xy chart, you give yourself a negative, I don't know, let's say negative 3, negative 2, negative 1, 0, 1, 2, 3, to kind of see where you're headed. So if I draw negative 1, negative 3, negative 2, negative 1, 2, 3, at negative 3 we're going to be at negative a third, so 1, 2, 3, negative a third is about right there. At negative 2 we're going to be at negative 2/3. At negative 1 we're going to be at negative 1. And then, like I said, at 0 we're undefined. So negative a third, negative 2/3, negative 1. Then at 1 we'll be at 1, 2, 1/2, and 1/3. So at 1 we're up here at 1. At 2 we're down at 1/2. And at 3 we're at 1/3. So for this part right here we can see that it's kind of shooting like that, and over here we can see that it's kind of shooting like that. But what we can't necessarily see is what's happening inside of 1 and negative 1. So we want to know what's going on in here. Well, if you think about the way a fraction works, the smaller your denominator gets, the bigger the number gets. Because let's say we had a denominator of 1, well then you're at 1. But then a denominator of 2 and your number got smaller. So again, if we did 1/2, say, well then our whole number is going to get bigger. 1 over a half would give us 2. So I could put that in and I could say at 1/2 we're actually up at 1, 2. And that gives us a little more. So then we start to see this pattern of shooting up our asymptote right there. And the same is true down here. So you have a hyperbola where you never cross the x or the y axis. Okay, so we have an absolute value function here, and no matter what x you put in, you're going to get out positive f of x values. So this should be some good review from Algebra 2 early on in our first semester in that class. And we can do an xy chart. xy, absolute value of x, negative 3, negative 2, negative 1, 0, 1, 2, 3. Absolute value of negative 3 is 3, so then we get 2, 1, 0, 1, 2, 3. So we're at 0, 0, 1, 1, 2, 2, 3, 3, and negative 1, 1, negative 2, 1, 2, and negative 3, 3. So there you go, your V-shaped absolute value function. Alright, so here is the second goal for the day. Piecewise functions. And the key is in the word there, piecewise. We're going to have one function made up of 3 separate functions. And really this part right here represents the 3 different functions. Over here, in red, this box that I'm creating, this is our different domains for each function. And what they do is they make it so that the entire thing is a function. Because if you graphed all 3 of these things, they wouldn't work together in one function. But when you restrict the domain of a function, then it lets you chop up pieces of a function. so that you can kind of put them together and overlay them. Alright, so first let's talk about evaluating. For A here, we want to evaluate when f is 0, or f of 0 rather, f of 1, and f of 2, and see what our values would be. So for f is 0, I'm going to plug in 0, but I got to look at my domain. So this function right here, negative x plus 1, works between 1 and negative 1, whereas f of x equals 2 works only at x equals 1. And then x squared works at all the x values that are greater than 1. So because 0 is between 1 and negative 1, we have to use the first function. So then I plug in 0 to the first function, f of 0, and I get negative 0 plus 1, which equals 1. F of 1, well, when you look at your functions again, that first function doesn't work because we're less than 1. We don't include 1. And the third function doesn't work because we're greater than 1, not greater than or equal to. So we can't include 1 there. The only time we can use where x equals 1 is this function right here. And we have a constant function of 2. So f of 1 equals 2. And then f of 2 is greater than 1. So we use our third equation. So we get 2 squared, which is 4. Alright, B. We want to determine the domain of f. Well, I think for these piecewise functions it's going to be easier if we graph them. So let's jump to C, and we'll use that, this should say range of f. But let's jump to C real quick. Alright, so first I'm going to look and see kind of where my boundaries are. And they're all kind of lying about 1. 1 matches everything over here. Excuse me, let me erase this. Alright. So what I'm going to do is I'm going to draw all 3, and then I'm going to kind of chop them up based on where they should be. So negative x plus 1, so I have a y-intercept at 1 with a negative slope. So it should look something like that. Okay? We'll call this function A, say. Alright? And then we've got a horizontal line, 2. Okay? And then we have a square function, or a quadratic function, x squared, which just sits at 0, 0, 1, 1, 2, 4, and 3, 9. So it shoots up like that. Alright, so first things first, we need to figure out where certain things work. If we call this function B and function C, we got B and C. Alright, function A only works between 1 and negative 1. And it includes negative 1, but it does not include 1. So I'm going to put a solid dot right there where that works, and then I have to erase everything to the left of it because none of that works. None of that's in the domain. Then I need to come to where f of x equals 1 for this function, and I gotta go put an open dot right there. And then I have to erase everything below that function, or to the right rather of that function. So I got an open dot. Then I look at function B. Well, it only works when x equals 1, so I actually have to erase the entire function except the point 1, 2. Okay. And then I look at my parabola, and it is supposed to be everything greater than 1. So at 1 I have to put another open circle and then the line connected to it. and erase everything below it. Sorry, I kind of erased my other stuff there. So you should have, you can see we have a dot here. That's our function b, where f of 1 equals 2. Then we kind of start our drawing at 1 for this guy, but it doesn't include 1. And we have part of our drawing for function a here, but it doesn't include 1. It just goes to the left from that spot to a solid point right there. Okay, so that's our first example of a piecewise function. We've got another one coming up for you. Oh, I almost forgot to add our domain and range from this. So we can see that here we don't have any function to the left of -1, and we have infinite x values to the right of 1. So my domain for this guy is going to include -1, but go to infinity. Okay. Or you could say all x's, provided that x is greater than or equal to -1. And then for D, our range, well, we don't include 0 here, we don't include 0 here where one of our functions hits, but we shoot from that point. So we're greater than 0, but not including 0. So you could say all y's, provided that y is greater than 0. Or you could say 0 to positive infinity, because there are no negative y values that come out of this thing. So there's nothing down here. Alright. Okay, so let's graph these. We got function A, function B, function C. Alright, so we want to go up 1, 2, 3, 4, 5. I'm going to go up 2 over 1, up 2 over 1, and up 2 over 1. Okay, so that's our function A. And we want to draw function B, which is f of x equals -3. And then we want to draw -5x. But if you look, function B here only works at x equals 0, so really it's only a point. So before we get all messy and have to erase a whole bunch of stuff, let's fix that up. Basically means 0, 3, the point. So or excuse me, 0, -3. So we're going to put that in. Solid dot right there. Okay, so then -5x, we start at 0, 0, and we go down 5 and over 1. And then we draw. Oof, that last bit was a bit ugly, sorry. Okay. And again, this part of our graph only works when x is greater than 1. So we need to erase all of this stuff. Open dot, and there you go. And then we have a graph over here that only works between 0 and 3. Okay, do me a favor and change this guy to -3. -3. That way we can make it look like a real function, because otherwise we had something screwed up there. So we need to put an open dot at 0. And a closed dot at -3. And erase everything else. Okay. There you go. So we got function A, function B, and function C. And our range, or excuse me, our domain would be -3 to 0, include 0, and then 1 to infinity. Make sure you include 0, don't include 1, and infinity doesn't get included. And then our range. So our range starts from -infinity and goes all the way up until 5 here, or excuse me, -5, but not including -5. So we would say -infinity to -5, and then it jumps to -3 here because there's nothing in between. So we have including -3, and then it jumps again to 0 all the way up to 5. So we have 3 intervals. Because we have no values between 0 and -3, and we have no values between 3 and -3 and -5, and we have no values up here, so our range is set. And there we go. Okay, one more piecewise function. 1 over x if x is less than 0. Well, that kind of makes our life easy. A reciprocal function looks something like this. So if you know the shape, you're good to go. And then the cube root function includes 0. Okay? And looks something like that. So they're kind of perfectly suited for each other because realistically, neither of them will cross once you separate them by the domain there at 0. So we've got a domain, and I'm looking at this domain and I'm saying, well, over here at -infinity, we're coming along, anything works, and then, oh, we don't get to 0, but this guy includes 0 and goes to +infinity. So our domain would be all real. Or you could say -infinity to infinity. And then our range, well, pretty much the same thing. We start at -infinity down here, we come up, get really close, but that one didn't do it. But then we start here and go from there. So we're defining a function based on 2 functions. And we have restricted their domains so that they don't overlap each other, and they can kind of be utilized together to create one whole function. So again, our domain would be all real, or our range would be all real. -infinity to infinity. Okay. Our x and y intercept would be 0, 0, which is the origin man. There you go. And give him some hair. Okay. Alright. Okay, lastly, we are given a graph and we want to write the piecewise function. So first things first, we need to write the equations and then we can figure out the domain from there. So I'm going to start with the left function, A, and then the right function, B. They both look linear to me, so we'll just treat them like that. A here, our slope is going to be 2 minus 0 over 0 minus -1, which equals 2 over 1, which equals 2. Then we have y equals, since this is a y-intercept, I can say, oh, well, I got 2x plus 2 then for that function. So then we have f of x equals 2x plus 2. Cool. Then for b, our y-intercept appears to be 0, 0, and it looks like we got a slope of up 1 over 1. So we've got function of x equals x, our identity function. So we're good to go there. Then you can see that right here we start at the origin and we start at x equals 0 essentially. So first thing I write is, alright, well, f of x is going to equal x and 2x plus 2, and in some form or fashion. But to me it only looks like this happens over here. This graph only happens when x is greater than 0. So this only happens if x is greater than 0. Whereas here, this is basically x less than or equal to 0, but greater than or equal to negative 1. Because there's no more of this function. It doesn't continue on to foreverness. It stops at negative 1 and goes up and stops at 0 in terms of x values. So our domain for something like this would be negative 1 to positive infinity, and our range looks to be about 0 to infinity. Alright. So again, we want to look at this and say, alright, well, where do we start? Do we include it? Because if it's an open dot, we don't include it. And closed dots, we include. And see where they go. But first, just write the function. Given 2 points, you can find the slope. You can plug it into your point slope formula, or if you can see what the y-intercept is, then you can put it into slope-intercept form, which is what I did here. And you write your 2 functions. Then you put them into a bracket, so they create one function. And then you look to see where they work. What x values work? Well, no negative x values worked, and we did not include 0. But we started at 0 in terms of drawing, so it was greater than 0. For the second one, nothing outside of 0 or negative 1 worked, but everything in between did, including our endpoints. So that's what that looks like. And now you've got f of x based on x and 2x plus 2 with their restricted domains. Alright, hope that helped, guys. If you have any questions, email me. I should be available. And I'll see you when I get back.